We introduce a multi-layer approach to accelerate the simulation of elastic solids with extended position-based dynamics. Our approach performs solver iterations on a sequence of approximate models. From mixtures of elastic and rigid parts with different percentages of rigidification to fully elastic. Rigid layers are built incrementally, always including the previous layer as a subset. See how the different layers use different shades of orange and change dynamically during the simulation based on strain rate. The choice of pattern is crucial. We compare random patterns, stripes, strain, and stretch-based patterns. Let's freeze. The layer iterations are first and use mixed rigid elastic systems, which have many fewer degrees of freedom and are much less expensive. The last iterations are fully elastic, strain rate, and stretch-based approaches converge more quickly. But the stretch-based layers are slower due to the assembly of the stiffness matrix. In this cantilever example, we observe that strain rate-based layers are cheap and reliable. The histogram shows the distribution of per-frame computation times for a typical simulation trajectory. Here, in the absence of pinning constraints, we include a fully rigid layer, and a purely rigid motion promptly converges to the correct solution. In these scenes where all the elements dynamically deform at once, our method shows speed improvement by using layer iterations. The speedups also scale with resolution. For a given vertex, contacts are solved as rigid during rigid layers and elastic when freed. This propagates the effect of contacts to distant elements, enhancing the stability of the solve, which can be challenging with XPBD when using large time steps. Here is another contact example using deformable capsules with green stiff sides and white soft sides, simulated with a relatively large time step size of 0.01 and discrete collision detection. In this final scene, many tentacles move independently. Our method improves convergence by coupling distant regions, effectively propagating large motions within tentacles. Thanks for watching.